Professor Pelton. This is part 2 of Chapter 1, Section 2. Now we're going to cover scientific notation, not to be confused with engineering notation, which is very similar. If you're in manufacturing, you'll see engineering notation. If you're in science, you tend to be seeing scientific notation, sometimes both. The important difference is this defined value right here of A. Come on, pen. There we go. Okay. The defined value of A for scientific notation is between 1 and 10, but you notice that it is not 10. It has to be a whole number value of a single digit, 1 to 10. Can't be 0, can't be 10, can't be anything beyond those. It could be 1.2, 1.3, 1.25, so on and so forth. And the number of decimal values varies depending on the application with significant digits. Okay. And the important part is um, the exponent. The exponent. Okay. Has to be an integer. It can be positive or negative. Okay. And those two inherent things differ it than engineering notation, because engineering notation has different a values and different rules for n. Okay, write the following numbers in decimal notation. Okay, so essentially what you're doing here is you're multiplying by 10 7 times. So this is -6, 5. There's one decimal value, and then 1, 2, 3, 4, 5, 6. So you've moved the decimal over to there because you've multiplied by 10 7 times. So my actual real value is -65 million. Okay. So the next one I'm really dividing by 10. So what this really means is 2.019 times 1 over 10 to the 3. So I'm dividing by 10 3 times will make you smaller. So 0.002 gives me the 3 place values I need, and then 0.19, which are the original decimal place values. So because I'm divided by 10, I need to get smaller by 3 more place values. Okay. All right, pause the video, try the student problems for yourself. Oh, I'm sorry, there's not student problems. It's more for me. Okay, then I'll have you student problems. All right, so you're going to write these in scientific notation. So basically, the decimal has to go from here to here, okay? Because I can only have one number, all right, between 1 and 10, but not including 10. So 0.497 times 10 to some power. So you have to think to yourself, this number here, right? Do I need this number to be bigger or smaller to get back to the original? Well, the original number was much bigger, so I need to make it bigger. Okay, so that means a positive exponent. So what do I need to go a positive exponent by? Okay, let's say different color here. So 3, 6, 9, 12 plus one more value is 13. So 13 place values to get back over to there, basically to get back to the original. Okay, so I'll make that 13. There we go. All right, so the next one, the decimal needs to go to there. So I have 8.2 times 10. Now the question is to get back to the original, do I need to make this number bigger or smaller? Clearly 8.2 is much larger, so I need to make it smaller to get back to the original. So by how many place values? Well, I moved it 1, 2, 3, 4, 5, 6, right? So I got smaller by 6 values, 6 decimal values, okay? All right, so divided by 10 6 times to get me back to the original number. All right, now pause the video and try the student problems down below. All right, so the first is writing them as decimals. So I'm multiplying by 10 9 times, so -26. So that's one decimal value. So if I multiply by 8 more, 1, 2, 3, 4, 5, 6, 7, 8, that gets me the 9 place values that I need. So 1, 2, 3 commas. What is that? Hundreds, thousands, millions, billions. Nice, so -26, 2.6 billion. Okay, so the next one, I'm going to write it over here. So 3017. Okay. So I need to divide by 10 6 times, right? So 3.017 times 1 over 10 to the 6, which means it gets smaller. So I have one place value, but I need to add 5 more, right? 1, 2, 3, 4, 5. So I can get smaller by 6 place values. So that is my new number. Okay. All right. Next ones. Writing them in scientific notation. Right, we'll just keep that there actually. Okay, so the decimal value currently is right here. You don't write it in the whole number, right? So I need to move it to there. So 5.21 times 10. So don't memorize left and rights. Memorize. Just think about size, right? Don't memorize. So this number 5.21 is smaller than the original number. So you need to make this number bigger to get back to what it's actually supposed to be. So that means you need to multiply it by 1, 3, 6, 9 values of 10 to get the decimal back to where it was. So if I multiply by 10 9 times, that'll make 5.21 back to the original number, right? Think about size, not left and rights and positives and negatives. Okay, next one. So 6.893 times 10. We have a negative on there. So I need to move the decimal from here to here. Okay. Which means this 6.89 is clearly larger than the original number as far as absolute value. So the number of place values I moved is 1, 2, 3, 4, 5, 6, 7, 8, 9. But I need to make this smaller by 9 place values to get back to the original. Okay, so that's our scientific notation. So let's do some operations now. Okay. All right, so if I do some operations, all right, what I need to keep in mind is this is all multiply. Whether you use the x or not doesn't really matter. It's all multiply. Okay. So when I write this, I can write 6.1 times 4 times 10 to the 5th times 10 to the negative ninth. Okay. It's all multiply, so the order doesn't matter. It's commutative, right? So if I do 6.1 times 4 separately, that's 24.4, okay? And this is times 10 to the negative fourth, because now we're using our exponent rules, which is to add exponents when it's a product. But the problem is this number is no longer in scientific notation. Scientific notation would be 2.44 times 10 to the negative 4. But I can't just simply move the decimal like that because these two things are not equal, right? So now I have to think about relative size. So my new number is smaller than the original number. So I need to multiply it by 10 to the 1 or just a single 10 to get it back to the original number. So they're actually equal now. Okay, so 2.44 times 10 to the negative 3 is the actual answer in scientific notation. Okay, let's do that same process for 1.8 divided by 3, and then 10 to the 4 over 10 to the negative 2 separately, right? So 1.8 divided by 3 is 0.6, and then this is the quotient rule, so this is 4 minus negative 2, so I get 6. Okay, so the problem is now this is not scientific notation, so if I move the decimal this way, I get 6.0 times 10 to the 6th, right? Erase that extra little arrow that I wrote there. But here's the problem. I can't just simply move the decimal. These are no longer equal, right? So the question is the new number is now too big. How do I get it back? Well, I need to multiply it by 10 to the negative 1, which is really dividing by 10. Because if I divide the 6 by 10, I get the 0.6 back. So now these are truly equal. Okay, so this is 6.0 times 10 to the 5th. Okay. All right, so the next one, C, power to a power, but that power or exponent goes to the entire power. So this is 4.5 to the second power and 10 to the 12th, right? Because power to a power rule is multiply. So we treat the number just as normal, 4.5 squared. Excuse me. So that's, let me think here. 20.5, right? No, that'd be 20.25. Sorry, I'm trying to do math in my head here. Times 10 to the 12th. Okay, so I look at this and 20.25 is not scientific notation. We need 2.025. times 10 to the 12th to be scientific notation. The problem being now is if they're not equivalent. So I need to multiply this by 10 to the 1 to get this to be back to the original number, which was 20. To make 2 back into 20, you need to multiply by 10. So 2.025 times 10 to the 13 is now, in fact, the answer, which is in scientific notation, right? All right, so don't just give answers. That's what people don't read the directions properly. Read the directions and make sure you give it in the proper notation. Okay, so next one is 6 times 3 over 2 times 4. We'll do those separately. And then 10 to the negative 6th, 10 to the 9, and then 10 to the negative 10, and 10 to the negative 5, right? It's all multiply, so we can change up the order as we please, right? So this is 18 over 8, right? And then 10 to the third over 10 to the negative 15, correct? So I'm using the power to a power rule to move the items around. Okay, so 18 divided by 8 is 2.25. 2.25 times 10, and then 3 minus 15 is negative 18. So in this case, it's actually already in scientific notation. So it's not true that we always have to do some kind of step to increase or decrease the number by a factor of 10 to get the answer. Sometimes it just works out nicely, just like this one. Okay. All right. So next is some example problems. What I want you to do is pause the video and try the example problems for yourself. Okay, so the student problems, again, they're all multiply, whether it's the x or a dot, it means the same thing. Although you shouldn't use the x out of scientific notation or engineering notation. Typically, you should use the dot. So 7.1 times 5, and then 10 to the 5th times 10 to the negative 7. Didn't get the negative into there. Okay, so do them separately. So 7.1 times 5 is clearly 35.5, which is not scientific notation, but that's okay. And then products, so I'm going to add the exponent, so I get 10 to the negative 2. So just rewrite the number in scientific notation. That's the first step, okay? And then don't memorize rules, think about size. That's the key to all of this. So 3.55 is clearly smaller than the original. I need to make it bigger by a factor of 10 to get it to equal the original number. Right now they're actually equal. So this is 3.55 times 10 to the negative 1. And now we've got it. Although my 5s aren't all that good. Okay, next one. 1.2 divided by 3, and then 10 to the 6th divided by 10 to the negative 3. Okay, so you can think of 1.2 as 12. So it's really 12 divided by 3, or basically 0.4, right? That's the equivalent. And then 10 to the 6 minus 3 is 9 because it's the quotient rule, right? But again, that's not scientific notation, so 4.0 times 10 to the 9 would be scientific notation, but the problem is they're not equal. I can't just change it like that. I need to make this smaller by a factor of 10 to get it actually equal to the other one because the original number was smaller. Okay, so 4.0 times 10 to the 8th is the actual answer. Oop, not a very good 8. I'm not sure that was much better. Okay, so just remember when there is an exponent, right, in dealing with powers, it needs to go to every term. So 2.25 to the third power, and then 10 to the, let's see, that's third, right? Yeah. So power to power rules multiply, so that becomes 24, right? 8 times 3. All right, so you have to think here for a minute. That's really 225, right? That's what it really is if I think about it. So 225 to the third power. Oof, that's a big number. So let's see, 11.390625 times 10 to the 24. Okay, so the problem being this needs to be 1.13900625 times 10 to the 24. But this number is smaller than the original by a factor of 10, right? So you multiply it by 10 to get back the original 11. So 1.13900625 times 10 to the 25th. And you don't really need all those decimals because typically in an application setting, you would know your tolerances and you would obviously round that off accordingly to the application of what you're doing. Okay, so lastly, so far I had to change each of these by a factor of 10, either larger or smaller, to get them into scientific notation. I believe this one you don't have to do that, right? So 5 times 4, 6 times 3, and then 10 to the negative 5, and 10 to the 8th, and 10 to the negative 11, and 10 to the negative 4. Because remember, it's all multiply, so the order doesn't matter. Okay? 2 times 3 times 4 is side 4 times 3 times 2, right? You can change it all around, right? So this is 20 over 18. And then let's see, product rule gives me 10 to the third, and this gives me 10 to the negative 15, right? Let's see, so 20 divided by 18 that's 1.1 repeating, so I'm going to put 1.1 with a bar above it. And then the quotient rule, well, the product we did first was add, so the quotient rule is subtract. So that's 3 minus negative 15, so that's 10 to the 18, right? Because minus negative 15 is positive. And look at that, we won. It's actually already in scientific notation. Okay, and that is the end of part 2.